Welcome back to Two Minds, One Model, a podcast dedicated to exploring topics in machine learning and artificial intelligence. I'm John Jezel, along with my co-host, John Rocha, and we're here at Sonoma State University's Department of Computer Science. This episode, we're diving into more fascinating AI research on this semester's main theme, interpretability. Let's get started. In AI and ML news, DeepSeek releases DeepSeek OCR model that uses virtual perception to compress text input. They claim to achieve 97% OCR precision at compression ratios below 10 times and 60% accuracy even at 20 times compression, comparable to state-of-the-art OCR performance. Meta is cutting approximately 600 jobs in its AI division, Superintelligence Lab. This is despite massive investment in AI infrastructure. Apple unveils M5 chip with 4 times AI GPU gains and 45% graphics uplift. This demonstrates a trend toward tuning consumer products to support AI runtime needs. And finally, Anthropic introduces Claude Haiku 4.5 as the default for free plans, combining low cost with high speed and extended thinking, and expands memory feature to paid Claude subscribers. Claude's memory feature, built on a form of retrieval augmented generation functionality, creates separate memories for each project to prevent context mixing. In our last episode, we dug into the geometric phenomenon superposition and how it causes the observable phenomenon polysemanticity. We discussed how phase transitions cause models to suddenly gain new capability at specific thresholds, as well as the geometric organization of how models arrange related concepts in high-dimensional space. In addition, we talked about the paper's use of toy models to demonstrate these things. We concluded by covering safety and interpretability concerns and what solutions were proposed by the paper. Today's paper explores decoding superposition using dictionary learning, one approach that falls into the third category of the solutions we enumerated in the last episode. Does the compression of these features back into something interpretable continue to work at scale? Anthropic researchers attempted exactly this using sparse autoencoders by performing a proof of concept on a tiny model, a step up from the toy model used in last episode's paper. So let's get into it.
Not so easy talking for long stretches, is it? So yeah, as mentioned, there were solutions proposed, theorized at the end of the last paper. Most of them came down to architectural changes that would restrict the preponderance of the model to hide features. And by hide, I simply mean store them lower than the surface. The fundamental premises, there are too many features to fit in the neurons, so multiple features get mapped to an individual neuron, which makes decomposing the activation of a model into this part of the brain caused this to happen a very difficult problem. You might ask yourself, why not build a better model that doesn't have those issues? And that's a fair question. That is one approach researchers took to solve this problem. So that's not a wrong question to ask. One of the ways that one might do that architecturally is a mixture of experts model, which is basically just you force efficiency by saying you can only use, an eighth, a tenth, some portion of your neurons each time I query you, each time you're asked to do inference as the model. This in turn reduces the likeliness of the model to store negative features that are as universally accessible, because the model cannot guarantee that it will always have access to that bad behavior. And a bad behavior is something like self-preservation. That's something it would want in all cases, not some cases. So that was thought to be a architectural aid to mitigating these negative behaviors. The answer to that obvious question, why not just design the network to not have that issue, is, yeah, cool. That's just not what they do in this set of papers. That's a different set of papers. So not an invalid question. It's just not the one we're aiming to answer here. Why not enforce sparsity during training, you might also ask. Similar reason as the answer above. Some have tried that approach. It's just not really the approach of this particular line of research. That sort of gets at why some other approaches aren't taken. And now let's get to this paper and the path it does travel towards as a theoretical solution to the problem of superposition. So one of the main issues is that enforcing monosemanticity means representing fewer features, which results in higher loss. Gradient descent, which is the training optimizing function for the model, will always exploit polysemanticity when it reduces loss. You can't architecture your way out of that without sacrificing performance. What that's saying is that because packing multiple features into multiple neurons makes the model perform better, it will do that no matter what architectural enforcements we try to impose upon it. That's well backed today with the empirics that mixture of expert models, which were more a theory back then and less an actual deployed production model practice, but is now a production model practice. Those are not as, but still susceptible to many of the same jailbreaking methods that normal, meaning non-MOE, non-mixture of experts models are vulnerable to. So it doesn't really solve the problem, but then again, nothing solves it. The best we get is a reduction in the chance. So the model prefers polysemanticity, meaning neurons don't map cleanly to individual features during activation. And the reason that's chosen is because you achieve lower loss with that capability, even if not told or trying not to. Any loss function that we define to grade the model on creates unmeasured dimensions. That was the negative space analogy I used in the previous episode about painting and how some painters are good at using negative space. Models will always exploit these gaps because it makes them better and makes the loss function lower, the price they incur for every wrong answer. That in turn leads to the paper's theoretical underpinning or a reason they went that particular direction. Like we mentioned in the solutions, there's a lot of theoretical directions you can go. They hypothesized that interpretability can't really be solved at an architectural level, so they are doing post-training analysis of a trained model. Essentially, they are using a similar intuition of mixture of experts, but importantly, a different mechanism. Mixture of experts is a gating function that decides which experts subsections of the network activate at runtime. It's a discrete top-down selection before computation happens. Sparse autoencoders, the mechanism we'll talk about and explain more today, is the same idea. Sparsity can restrict this tendency towards superposition and thus make the model more interpretable. For sparse autoencoders, the layer 1 penalty incentivizes sparse activation. And here sparsity means not the infrequency of activation like last episode. Here sparsity means of the ideas, words it has in its dictionary, it will be restricted to only being able to utilize a subset of them. And all the other weights are turned completely negative. And that penalizes the model for doing polysemanticity. You basically tell it if you ascribe your processing to too many zones of your brain, we're going to punish you. And that's in turn sort of decompresses the polysemanticity into monosemanticity.
I wanted to butt in here. You mentioned level 1 penalty. You were referring to the L1 penalty,
L1,
which is
layer
not
1.
Layer 1 penalty.
Yes.
It's just a mathematical technique.
Yeah, you're right.
So I just wanted to clarify.
Loss.
Yeah, that was actually my assumption when first saying the term as well. So that's a little misleading.
That's why you're here. I mean, and all these terms with notations, no one remembers them all. Let's be real. That's what the internet's for.
For sure.
The L1 penalty pushes the learned features themselves towards monosemanticity. Sparse autoencoders are about representational clarity. I'm finding the features that were supposed to be in the original model. It gives you a clear space for each feature rather than saying, oh yeah, that ability to do X, that's kind of spread over 100 different locations. Now let's talk about sparse autoencoders, the technical mechanism used in this paper. Really, all an autoencoder is supposed to do in this context is a data compression mechanism that aims to reconstruct from the compressed form actual behavior. You can probably already see where that's going. It imposes bottlenecking forces to impose the rigor of learning the most visibly active features. Now, what makes it a sparse autoencoder, and not just an autoencoder, is that L1 penalty that's on a hidden layer. So now you know why it's not called layer 1. So it adds the L1 penalty on a hidden layer to not make it gameable. The idea is to reduce gameability. It forces most features to stay at 0. That also reduces the interference from other neurons, other features, other capabilities of the model. If we can reduce the concurrent activation of other parts of the brain, we can with more confidence say that part of the brain is responsible for this part, this function, this behavior. The point is to force at inference time only relevant features to activate. This makes it easier to map out where the features lie in this or that part of the model, and as we'll see later, it allows you to have some cool control mechanisms. So the counterintuitive sort of direction here is the model in this paper has 512 neurons, up from 5 in the last paper. So this is a couple order of magnitudes bigger. Similarly, there's orders of magnitudes bigger is the feature set that we're trying to teach this small tiny model. So we want to create from a 512 neuron trained model, we want to create a smaller model in neuron count that has a fixed dictionary size of capabilities, of skills, of words. A dictionary. Dictionaries have limits. So by artificially imposing via using the trained model to train our sparse autoencoder, we go from 512 neurons to 131,000 directions in a high dimensional space. That's what you should think of when I say dimensions, like navigationally useful information in a complex space to navigate. That might seem backwards if the stated objective is compression, but we might be compressing neurons, but we're decompressing features, the superposition of the neurons. We're trading lower neurons for more discernible behavior because we impose an artificial limit of you can have this many features, and via the L1 penalty, you can only activate n of them at a time, 5, 4, 8. The point is, by forcing sparsity, the tiny model you train to predict accurately the behavior of the larger, in this case, 512 neuron model, training that model, we are giving up the smaller neuron count for a more cleanly defined dictionary of possible behaviors. This basically greatly reduces the danger and frequency of the superposition phenomenon that we described last episode. So the math here, as I describe a few of these terms, just remember the key point is high dimensional activations are meaningful. That is the behavior of the compressed model. They're superposed features. That means they're features that exist not in a discrete space, but somewhere across a lot of space that we don't really know exactly where yet. Sparse autoencoders try to find the true feature basis in that lifted space. That means they try to reduce a given geographic space down to you only activate during this. Like, what makes you activate the most frequently when looking at a particular set of neurons. The objective is make superposition more costly to disincentivize the model from doing it. That's what the L1 factor is. The network isn't randomly projecting what it thinks the bigger model might do. It's learning geometry where semantic concepts align with directions. And hopefully that makes sense, that mapping of a coordinate system, they're mapping it to the abstract concepts we learn in language, like homophones or whatever other linguistics or whatever. The point is that we're creating a geometry, a more defined way to navigate around a complex space than we had before. The network isn't randomly projecting, it's learning a geometry where semantic concept aligns with directions. I think we used the example last time of the difference in this high-dimensional space between man and woman is very similar, is a very similar vector as uncle and aunt, exactly.
Yeah.
So that sort of illustrates that, like, gender of a word is one of those directions. One of those.
I'm curious if you have a language where nouns are actually gendered, like French, where a noun can be a masculine noun or a feminine noun.
Does
is there an effect of the? Does that?
I would say probably. It would.
I've never really thought about that.
It definitely. Yes. The short answer is yes. The long answer is yes, but we don't know to what degree exactly.
Well, sure, and because two gendered nouns can be completely unrelated, and how do you normalize that?
That, and on top of that, if 90% of our training data is in English, can we really say that, like, the model is bad at doing, or if we had trained it from a same size corpus of data in Korean or French or whatever, might it have a different sense of gender as a result of being trained on that language? It definitely would.
Something to ponder.
Yeah. The point is that until every country has hundreds of billions to dump into teaching a language model with their only their language, this is kind of just a benefit of being I'm trying to not say hegemon, but I'm just going to say it. The global hegemon. That's just one of the perks, is that, I'm going to stop talking about that. All right. The point is that at the end of the day, after all the math, after training, that the sparse autoencoder minimizes reconstruction error. That is the difference between what it thinks activation is going to look like in the model versus what the actual model's activation is when you're testing it. That's the function that the sparse autoencoder is trying to minimize while it's being trained. So the insights here are that each learned feature is a direction in the original 512-dimensional neuron space. Sparsity, that is the sparsity we talked about earlier, which is constricting the model from attributing to multiple positions its behavior by saying your pointing can only be so vague before I'm not taking your pointing seriously anymore, basically. And that sparsity forces features to be monosemantic. There's also approximately 10 features active per input out of thousands. That is to illustrate that this does achieve monosemanticity relative to the dictionary size that we give it. And you'll see why that's not one-to-one and why there are caveats there and why you're hearing the caveats, even in my intonation probably. Because, this is, after all, fundamentally a experiment on a tiny model, and a novel approach at that. So the sparse autoencoder is architecturally just a one-layer transformer. It's 512 neurons in a multi-layer perceptron layer, an MLP layer from here on. I'm not going to say multi-layer perceptron every time, MLP. So 512 neurons in an MLP layer, standard attention plus MLP structure. Attention is the notion that in the position of the words you choose, there is some conferred meaning. The MLP structure is a little more what we think of when we used to think of the brain as simple neurons that are either firing or not firing. Frequent firing of a certain part of your brain reinforces the activation of that area.
Would it be useful here to maybe give a 30-second rundown on what a multi-layer perceptron is?
Sure.
'Cause I don't think we covered that.
We kind of talk about it in the history, or if I didn't, I failed to talk about it in the history episode. But in the history episode, that actually multi-layer perceptrons are very old, and they predate expert systems even. Basically, they were the earliest form of neural networks. They were feed-forward, backpropagation, which is just calculus for learning from error.
So
It's the earliest set of neurons and weights connecting all the neurons' data structure.
So
it's the simplest.
Backpropagation as
is
you're
a training
feeding the training
mechanism.
data through, you're taking the end result of that as the training data goes through and providing corrections to
you use that as signal.
Yeah.
It's propagated back. Mm-hmm. Yeah. So the MLP was like the first simplest data structure where they were like, okay, we're going to try to mimic the brain. Let's make a few neurons at each layer. Mm-hmm. Let's connect them to all the other neurons and then use this cool subfield of calculus to inform the training by saying, hey, if you get this right, you get a digital cookie, whatever.
And it's built basically of a top layer, a bottom layer, and the top layer is where the input comes in, the bottom layer is where the output comes out, and in between there are these hidden layers, generally a couple of multiple hidden layers.
Yeah, hidden is a strong word, but I hear what you mean.
Yeah, it's not exposed to the input or the output.
Not directly, but the connections do mean that all activations influence all subsequent activations.
Okay.
If you took out a random layer, one of those hidden layers, the activation would be different.
Right. Yeah.
So kind of.
Right. Yeah. Hidden from view, but not from function. Yeah. So anyway, I just wanted to do a little recap on what MLP was,
and transformers are complex.
They are
versions of MLPs. Yeah. I mean, they use
compound
the same very compounds, and there's some normalization. But anyway. So the training data for this, tiny. I keep wanting to say toy because they both start with T. I should have thought of another word for small that didn't start with T.
Little
model, yeah.
Although that's probably got another specific definition too.
Yeah, probably.
Teensy? Oh, no. Whoops,
yeah, another
work.
T. Why are all the small words T? Anyway. So the training data was given some, what you might call normal training data, like just raw text. A diverse text corpus and real language, nothing synthetic. That means they used cleaned data to train the comparison of the sparse autoencoder to the tiny model's activation. Now, one of the key innovations that made sparse autoencoders work in the first place is something called neuron resampling. But let me clarify something important first. In regular neural networks, you get dead neurons that stop firing entirely during training. Like, basically, they're stuck at zero forever. And that's not the dead we're talking about here. Shout out homophones or homonyms, whichever one fits here. Yeah.
Not quite either. Well, dead.
That's... for the
all right. Well,
I'm just making work for you, the editor.
Good times.
That's not the dead we're dealing with here. In sparse autoencoders, we have dead features, which is a different problem. In this paper alone, we've expanded from 512 neurons to 131,000 features. The L01 penalty, the tax on using features, is so aggressive, so high, that most features will never activate. Their activation, when prompted, will be negligible. They're not turned off in any way that we might conventionally use that phrase. They just are never worth the cost of using and are therefore invisible to our interpretability devices. Think of it like having 131,000 specialized tools, but the rental fee is so high you only ever use 10,000 of them. That's 121,000 specialized tools all engineered and manufactured and shipped to you and sitting in your garage unused. Anthropic's neuron resampling essentially fixes this problem. Ever so often, the system checks which behaviors, features, inputs are we reconstructing poorly? Are we doing a bad job of deciphering? When it finds one of those that it's doing poorly at, it takes the dead feature and it reinitializes it. It randomly sets the wheels and knobs that you can imagine in the model's brain. It reinitializes them specifically to help with those hard cases. It's basically like telling the model this specialized tool for detecting, I don't know, something as minute as ancient Sumerian, poetry isn't being used. Let's repurpose that space to detect a different feature because that turns out isn't worth being distinct enough to be a feature worth detecting.
Ancient Sumerian poets will be offended.
Yeah.
All of them listening right now.
Right. I think ancient is enough to get plausible deniability our way out of that one. So you might ask yourself, why does this matter? Well, because the fundamental objective of this research is the need to locate behaviors in a discrete geometric space. If the model has learned deception or manipulation or backdooring code or any other dangerous behavior, we need to know exactly which feature, which geometric space encodes that behavior. Once we can point to specific features and say, this is the deception feature, we can dampen it, amplify it, or remove it entirely. That's the whole game here, turning the tangled, inscrutable mess of superposition into discrete, addressable features that we can actually control and not just pretend to control. And I promise we'll see shortly why that's so important and why we keep looking for a discrete set of space to attribute to a behavior of the model. Spoiler alert, if you dampen that section, it reduces the model's willingness to do that behavior. And that's obviously has benefit from a control mechanism point of view. Fundamentally, we're going to need to be able to ascribe functionality to a location in the device. I mean, that's a pretty basic thing that we might take for granted in different technology.
It's funny how after researchers do all this work, it seems so intuitive.
Right?
We stand on the shoulders of giants.
Always. So neuron resampling is basically just a solution to that dead neuron issue, features that are lost because they're represented in multiple places, features that never activate waste capacity, therefore they get pruned, you can think of as a pruning process. The traditional solution was pretty much just eat the waste because they're great elsewise. Anthropic solution in this paper is essentially use the Sparse Autoencoder to monitor feature activation frequency, identify features that never fire, i.e. those for pruning, reinitialize them from high loss examples, meaning retry, take a very bad attempt, use the worst failing as you can as a teacher, basically. That gives a stronger signal to the backpropagation learning system than where it got it slightly wrong. This gives them another chance to learn. This ensures all 131,000 potential features stay alive and learnable with our sparse autoencoder, that is our reconstructive tool for the behavior of the production model. It's like replacing broken wiring in their brain. Here's just a short list of some of the discrete features that they found when reducing the small language model to a feature dictionary, to a set of features that correspond to a discrete space in the network. The ability to communicate in base 64 and HTTP headers, in Korean, in DNA sequences, academic citations, HTML tags. You get the picture. The real benefit here, and I already kind of spoiled it, but features are causal. If you take the space that you know is always active when base 64 is invoked, and you turn the activations way up, the model is always going to respond in base 64. Or, if you turn the Korean section way up and academic section way up, it's going to have the same response. The model's always going to answer in Korean. If you wait put your hand on the scales, I guess is a good metaphor.
That is a good metaphor. I like that.
And like I mentioned, it's good as a control mechanism because conversely, if you dampen the activation of a specific location, you greatly reduce the model's capability. In this tiny scenario, you all but solve it. You do functionally solve it with a tiny model asterisk. For example, if you say all the base 64 neurons, their activation gets a -1 coefficient. That will mean even if you ask the model to do base 64, it won't be able to. And that is a useful control mechanism. And another benefit from this sort of discrete mapping of features that dictionaries, that sparse autoencoders help us achieve, is the compositionality of features. For example, Korean and academic, for instance, are two features that can be concatenated in this space to inform a geometric dimension that corresponds to Korean academic text. So it understands both that you want Korean and that you want academic level sources or thoughts. And if you activate these two features, you can be certain that what you're going to get is Korean academic text. Features interact as expected. That is basically saying if me or you were to talk to each other and said, hey, talk to me in Korean and academic text, presuming we both knew Korean, or either we're academic, or either of us were academics, that those two features map coherently. It's not like I'm saying Korean and cord or pen, not two disparate, unrelated concepts. Right. Two concepts that make sense in a compositional way to form more complex concepts, like a language plus academic writing. The point is that after performing this decompression of the neurons into mappable features, we basically can now identify with certainty where a feature is, what part of the brain of the model is active when asked this type of question. We can identify those features now, and that in turn gives us the ability to pin the features to increase the coefficient of their activation or decrease it. That allows enforcing and what's the opposite of enforcing? Deterring? Deterring bad behavior and encouraging good behavior, or wanted behavior. I won't even say good or bad. It also allows us to observe model behavior changes, and behavioral changes match feature interpretation. Like I said before, Korean and academic is a sensible pairing. Lamp and, sticker are probably not as related. Like if I were to give you two keywords before our talk and they were sticker and pen or something, you'd be like, what, is this guy okay? Is he having a stroke?
Do you smell toast?
Yeah. But if I said, let's have an academic discussion in English, it would be weird, but he would understand what I meant. So that's what we mean with behavior changes match feature interpretation. We think our dictionary is sensible. Now let's move on to interpreting the interpretations. You like interpretation? Let me interpret your... Anyway. Geometric organization by semantic similarity. This is essentially text formatting features clustered together. Programming languages are also co-regional. That might be the right word. In this high-dimensional space, they're clustered together. That's what would be a good word for cohabitating? I don't know.
Co-locating?
We already determined proximal is not. We weren't using that one, right? So I won't say that. But
in close proximity.
Close proximity to each other. That's all you need to understand is that features that make sense to be together, like programming languages or languages, like those features all are closer together than disparate features, unrelated features. That's the real takeaway here. This validates the intuition from the last episode that the geometry of superposition isn't random. Like we knew that there was some sense to it because the overlapping made sense. The less frequent a desired behavior arose, just like in our brains. I'm trying to think of something really obscure I learned, but I guess I can't. That's kind of the point. The point is, like, if you don't need to know the information all the time, you're going to forget calculus pretty fast, is the point.
My calculus was over 30 years ago, so
and I bet
I don't remember much of it at all.
I just didn't want to besmirch calculus as a intellectual endeavor. It is very valuable and fun to learn,
without question.
But it's not. Let's be real. It's not frequently used for most people, and therefore, similarly for a model, things that aren't asked of the model frequently are difficult to find, are difficult to attribute to a specific location when they do arise, because the activation is more spread out over a bunch of neurons rather than cleanly visible as a difference in activation. All of the neurons are lit up a little bit, instead of, hey, these 5 neurons are blaring red lights saying, hey, look at me, you know what I mean? It's more clearly attributable to a discrete set of neurons.
Right.
So the fact that semantically similar features cluster in the learned representation space confirms that superposition isn't random noise, it's structured compression that organizes features by co-occurrence patterns. There is still, however, the completeness problem, that is to say, like compression, lossiness? How much information is lost when compressing. That information is lost when compressing is a version of the completeness problem. So like, even though we expanded the number of possible entries in the dictionary to be 256 times the number of neurons, it still doesn't capture everything. That's part of the point and part of the problem. If we're going to capture everything, it would be computationally prohibitive. If we didn't capture everything, then we can only say with certainty we have control over the top N features. And the problem is, if the bad behavior is the N+1th common feature, that is going to get lost. It's going to get pruned, it's going to get chopped off, and that part might be good. But so too will all features N plus I will all get pruned also. And some of those you might occasionally need, like calculus. You may even need that one day. It's probably good to know something about it.
Sure.
Even if you don't use it every day. So
sometimes it's good to just know the concept.
Yeah. Continuity versus discontinuity. It's a very cool, you know, even if you're not doing integrals every day. The reconstruction error remains, and some behaviors remain unexplained. So at least to the researchers at this point in time, this paper is a couple of years old at this point, which in machine learning research is millennia. So I imagine the authors would say something different now. But at the time, it was uncertain if this approach would scale. This was the first significant foray into this theoretical path to solve what we observed, superposition, polysemanticity, in language models. But it's not all doom and gloom. That is kind of expected. Like, if the sparse autoencoder could do everything the parent model could do, we would just use the autoencoder. If it wasn't helpful in mapping the geographic space to concepts that are parsable by us, we wouldn't be talking about this paper, because it would have been a failed research idea, not a paper. So, you know, it would have been just another discarded hypothesis. Even though what's missing in the completeness problem might sound like a big caveat, it's not really. Like, it's a very academic way of saying, if you want control mechanisms to persist, you better give the safety guys as much money as you're giving the capabilities engineers. And that's sort of the core thesis of safety research in general is, cool, these things are getting good, like, we agree, okay, but also it might be good if, you know, we could tell why the Waymo car ran me over. That might, you know, help my family or someone mourn, or the opposite of mourn.
Give them closure.
Yeah, closure, sure. I didn't. Glee is more. But anyway, so there is a trade-off. You do get benefit, but it is not a 100% take this to the bank solution. I would not trust it for a life and death situation. But, you know, and again, this is on a tiny model. Small? What did we settle on? Non-T? Because I keep wanting to say toy. Scaling it is the next challenge. Gee, I wonder what paper we're going to talk about next. Hopefully it's clear that although creating these sparse autoencoders is a very, very computationally expensive task, that unless for some reason, I'm trying not to get too into politics or economics, but why no research lab who's fighting for investment dollars by staying competitive in the benchmarks and how capable your model is, why none of them are going to take the kneecapping that would be, hey, devote 50% of your compute to make sure you can enumerate the behavior in relation to the location of activations in the network.
Right. They need a compelling reason, business-wise, to spend that kind of money. And
until either a sane government...
You could be jaded about the reason why or not, but I think it boils down to that, right?
Absolutely. This is the trade-off that has Geoffrey Hinton, that has famous deep learning researchers talking about catastrophic repercussions on the news that you probably see as dramatization. But that's kind of the thought there.
Have you seen the Jon Stewart interview with Geoffrey Hinton?
No, but it has appeared in... I haven't seen it because I've seen enough of his interviews that I know exactly what it's going to be.
Sure.
Well, not exactly. I've heard him speak a lot, but I saw he gave one. Was it good? Did you see?
I felt it was very good. I felt it was a very approachable interview, and I encourage people that are interested in this sort of thing, that are in that zone of needing a more approachable point to start at to understand the problems here. Go check it out. He's not only extremely intelligent and presents a very understandable and approachable...
He's also the inventor of backpropagation.
They call him the godfather of AI, apparently. Anyway.
He is one of the top 3 cited researchers of all time in AI. I mean, every paper with learning cites backpropagation.
Yeah. He also has a pretty wicked sense of humor. So, yeah.
Very cool guy.
Anyway, carry on. Hopefully I didn't throw you off too much.
Not at all. I have an outline this time.
I'll try harder.
Believe it or not. Geoffrey Hinton is the famous one. Blake Lemoine. He was one of the first engineers to what is now so common that it has a colloquialism, AI psychosis. You know, he was one of the first persons to have issues grasping the difference between conscious humans and their interactions with a text model. That's, I think, as kindly as I can. We've sort of talked about the trade-off problems with this approach, next steps, but to take a step back for a moment and ask ourselves why these results matter, what these results demonstrate in the larger scheme of assessing deep learning as both a threat and a capability of mankind's, it demonstrates a few things. It proves some things. Superposition is decodable. That's one of the first things it proves, that it's not a mystical or intractable problem. That's probably not a surprise to most of you, but given enough time, money, and compute, we can do it. That might not sound super cool or good, but it is comforting knowing that the only thing holding us back from safety is our lack of willingness to do safety. I do find some cold comfort in that, despite my tendency to agree with Hinton's perspectives. Check his interview to ascertain what I mean by that. I'm sure John can.
Link in the description.
Yeah, thank you for the, that is the hip way to say that. The fact that this proves superposition is decodable is, despite the jokes, is very powerful. That is a very noteworthy thing, that we can decompose superposition into definable features to the point where we can dampen them. We can make them not able to handle base 64 anymore because we put the kibosh on a specific subset of the circuitry of the brain. Like if I bonked your head in the right way, you might forget to be able to do calculus or whatever, some skill you can do now. That's not the point. So superposition is decodable. That's very cool and helpful and good for control research, for safety research, for legislation, for just use in workplaces, for all of the reasons that the EU is sensibly, in my opinion, but I'll leave it to others, regulating the deployment of AI in different domains intersecting with human life, is because Obviously, if we can't say why this thing did something, but all it is chatting at you, that's much more forgivable than if it's controlling a vehicle that can run people over. Or it takes in resumes and determines who gets a chance at a job. Yeah. That's kind of a serious thing.
Yeah, the stakes are very different.
That we should not take lightly. Mm-hmm. And unfortunately, as to Hinton and my lament, Hinton and I's lament?
Hinton and my, because you would say my lament.
Linguist in the studio here, folks. Or guy who paid attention to 12th grade English. Pick one.
Had a mother who had a master's degree in library science.
Yeah. Superposition is decodable. That's good news one. And result one. That is the key takeaway headline here. Hey, it's solvable. It's not a mystical, spooky, we don't know what's going on. What did Einstein say about spooky action at a distance?
Oh, right.
It's not spooky action at a distance. It is a decodable byproduct of the compression that happens when we squeeze too much thinking into too small of a space. Also, it demonstrates if every feature we looked at had no consistent pattern of activation in the network, this approach would be fruitless. But because upon that clamping down of spurious half activations, because of that L01 loss that we randomly impose, we get real mapped features. We get a discrete set of locations in the model that we can point to and say, hey, that's the base 64, that's the Korean, that's the academic text feature. We know because if we turn it off, it can do everything but speak Korean, but speak base 64, but cite texts or whatever the feature that you're dampening the activation of. Or more realistically, all you're doing is you're appending extra cost to the activation of those neurons. And therefore, those neurons won't activate because the model doesn't want to have its digital cookie taken away. I know we use that metaphor for the reward, but I don't know what's the digital equivalent to getting you shocked, I guess. I don't know. Anyway, so features are real, superposition is decodable, and interpretability is possible. Those are the three biggest takeaways. Interpretability research isn't just correlation hunting. It is what conventional engineers might call a mechanistic understanding, a real discrete understanding like you would have if you looked at the schematics of a PCB or something. Like it is a relatively fair...
Printed circuit board.
Oh, yeah, sorry, I forget. So, yeah, this does give us actual mechanistic understanding, and that causal intervention works. We can put a clamp on this set of features should we discover them, and it stops doing that thing. All of these are very helpful results. That is why this paper is obviously exciting and important, and this subspace, this approach to sorting out the problems that language models have as far as bearing scrutiny and being controlled. As always, if you read papers, you know there's a limitations section. The limitations are there. We sort of talked about them. The completeness problem, that's the main one. What this doesn't solve yet is complete mapping. It's just not complete. This will always be a partial reconstruction, a sparse one, you might even say. It's only demonstrated so far on toy model, tiny models. Totally different, I promise. Tiny models. The computational petite models. That's awesome. That is the computational overhead of doing this discovery is massive. It is problematic. Computational overhead is massive. We can't find specific deception circuits, or circuits being a set of neurons, meaning more than one, because they're wired together, we call it a circuit. We can't find specific deception circuits. That is, when we do observe bad behavior, we don't see it in a specific location yet. It's still more of like one of those super features we described, meaning the feature is not a discrete subset of the network activating very strong enough to point and say, hey, that's that. It's more like a 1% activation spread across 50 different locations. That's part of the problem. If we have a dictionary of 130,000 things, the 132nd thousand is still going to be cut off. So it's more expensive. It doesn't solve everything, which is not going to be a boon in their hat when their hat is turned upside looking for money. So next episode, just to give a short preview, this was in 2023, which is almost 3 years ago now. What happens when we scale this approach to a production model? For example, Claude Sonnet, to not choose any company in particular. What happens when we scale it up to observing millions of parameters instead of 512, to models that actually matter? Next episode, scaling monosemanticity. Spoiler alert, they found features for deception, sycophancy, bias, and more fun stuff.
Sycophancy, if they could get rid of that, I'd be very happy.
Me too. I literally have, in my system prompts, I have what measures can be taken against sycophancy.
Right. Mitigations.
Right. Mitigations, thank you. They found abstract concepts like inner conflict and philosophical reasoning. The proof of concept worked. Now let's see what happens at scale.
Yes, today we saw that superposition, the seemingly impenetrable compression scheme, can be partially decoded. We can take the compressed, entangled mess of polysemantic neurons and extract interpretable features. Is it perfect? No. Is it computationally expensive? I think we made that abundantly clear. But it works. Remember the episode 2 fears about MESA optimizations, about hidden goals? We just saw the first step toward making these fears checkable. We can start to look inside. The real question isn't whether we can decode superposition anymore. It's whether we can do it fast enough, at scale, and on models that matter before they become too powerful to control. Next time, we'll scale this up to Claude 3, and we find some genuinely disturbing things. As always, remember that any references we make in here, I'll do my best to put a link in the description. And that wraps it up for another episode of Two Minds, One Model. Make sure you subscribe to the podcast to avoid missing any episodes. Thank you for listening, and we'll see you next time.